Okay. Chapter 1 of the organic chemistry is basically a review of what you have learned in general chemistry that is applicable to uh, organic chemistry. So we are basically reviewing some sections of the chemistry that you have learned so far. When we talk about chemistry, what makes the organic chemistry different from other chemistries? Organic chemistry is a study of carbon-containing compounds. How many elements do you have in the periodic table? Do you know? It's supposed to be like over 100, right? 112. Some of them, they have no name. That means IUPAC has not decided on their name yet, but the element has been discovered. So if you look at the periodic table at the end, you see only numbers, you don't see name. That's why. The inorganic chemistry is the chemistry about 100 other elements. Organic chemistry is chemistry of carbon, and it's basically carbon, hydrogen, and carbon and its carbon-containing compounds. And you have two other numbers that we talked about: 16 millions of organic compounds and 800,000 of inorganic compounds. Can you put these two together? How could one element from periodic table be responsible with so many elements, so many compounds of organic, versus 110 other elements just for 800 or 900,000, less than 1 million? That shows how unique is carbon. So organic chemistry is a study of carbon and its compounds. What is unique about carbon? What level of periodic table is carbon? Can anyone tell me? You could use the chat to answer the question. Second, very good. Second level of the position of the periodic table is in the second level and group 4. Any elements in group 1, 2, and 3, they lose electron. Any elements in group 5, 6, and 7, they gain electron. Elements in group 8 of the periodic table or noble gases, they are the model or role model for other elements. Every other element wants to be stable, just like noble gases. By sharing, giving electron or accepting electron, they want to be stable. So carbon being in group 4, it shares electron, it doesn't lose electron, it doesn't gain electron. So what else is unique? Carbon is tetravalent. Carbon can form 4 bonds. Carbon is happy when forms 4 bonds. Carbon is not stable with 3 bonds. That means it's missing 2 electrons. Carbon is not stable with extra electrons. Carbon would go into disaster mode, very unstable, if you put 10 electrons around carbon. Why is a disaster? Why is very uncomfortable for carbon to have more than 8 electrons? If you told me already carbon is in group level 2, that means how many orbitals you have in level 2? In level 2, you have only s and p orbitals. How many electron goes into s orbital? Can have your chat open, just put the answer at a no. Very good. And how many electron you have in p orbitals? Total 6. So that adds up to 8 electrons. So any element in level 2, that is nitrogen, oxygen, fluorine, carbon, cannot have more than 8 electrons. So carbon cannot have more than 4 bonds. 4 bonds is the satisfaction or the best thing for the for carbon. That's why it's called tetravalent. Carbon can form different hybridization, hybrid, sp2 hybrid, sp hybrid, or sp3 hybrid. When all bonds are single, so carbon forms 4 single bonds, the hybridization is sp3. When it forms 1 double bond and 2 single bonds, is going to be sp2. If it forms 1 triple bond, then the hybridization is going to be sp. This is going to be, one of these is going to be question in your quiz, and another one is going to be question on your exam. So being able to determine hybridization for a carbon is going to be questioned. You will see them in the assignment, you will see in co-op, you will see in your quiz, you will see in the as exam, and you will see in final. So pay attention to what is why carbon is unique. So carbon can form single bond, can form double bond, can form triple bond. Carbon can form bond with other carbons. So with other carbons as a single, double, or triple bonds. So carbon is very unique because of that. The type of hybridization that can form, the order of the bond that it can form, and the carbon-carbon chain. Carbon chain is known for organic chemistry, is known as the backbone or a skeleton of the molecule. Let's say you have ethane, so you have like a CH3CH3 for ethane. The carbon-carbon single bond that you have here is going to form the backbone of the molecule. For a cyclohexane, when you have like 6-member cyclic system, this carbon skeleton is going to form the backbone of the molecule or represents the carbon skeleton. So the carbon-carbon bond in organic molecules is going to be the number of carbons that it's connected to each other. What else do you remember from inorganic chemistry about the atom? And our focus is going to be atom of carbon. Carbon, what are subatomics for carbon? Can you tell me subatomics for carbon, please? When we say subatomic carbon, subatomic particles, that is number of electrons, number of protons, and number of neutrons. So when I ask you for subatomic particles, you must say which carbon you're talking about. Are you talking about carbon-12 or you're talking about carbon-13? And very good, yes. So we have 6. 6 was what for which one? 6 for all? If it's a carbon-12, then you have 6 electrons. Very good. You have 6 electrons, 6 protons, and 6 neutrons for carbon-12. For carbon-13, what are the subatomics for carbon-13? For carbon-13, 6 electrons, 6 protons, and 7 neutrons. So 7 neutrons for the 7 neutrons is the only difference between carbon-12 and carbon-13. How these two are related? They are isotopes of one another. So different number of neutrons, but the same number of protons. Atomic mass is the number of protons plus the number of neutrons. And atomic number is just the number of protons. How is number of protons related to number of electrons? Number of protons always equals to number of electrons in a neutral atom. If the atom is neutral, number of protons and electron is the same. If you change that, how could you change this? Number of electrons can be changed or number of protons can be changed? I guess I'm waiting for an answer. Which for a given element, for atom of given element, which one can you change? Number of electrons or number of protons? Can you change the number of electrons? Yes. Can you change number of protons? Can you change number of protons? No? Yes? No. You can only change number of protons in nuclear reactions. If you change the number of protons, that means you are changing the mass of the atom. You are changing the number of protons, so the identity of the compound or the element or the atom is going to change. And when the identity is changed, the mass number is going to change because you are changing the nucleus of the atom. That's why it's called nuclear reaction. So what you have inside the nucleus of the atom is the neutrons and protons. That's in the nucleus. The other name for nucleus of the atom is do not touch it, because if you touch it, it's going to cause so much of energy. It's going to produce so much of the energy if you touch the nucleus of the atom. So you cannot change the protons because they are inside the nucleus. But you could change the number of electrons. Electrons are donated, electrons are accepted for elements to be able to achieve the octet satisfaction. So the element like sodium has 11 electrons. For neon has 10 electrons. Sodium is going to lose 1 electron in order to be just like neon, based on the number of the electrons. So number of electrons can be changed, but number of protons cannot be changed. The atomic orbitals. What are atomic orbitals? Atomic orbitals, you know them from general chemistry, s, p, d, and f. Level 1 has only one orbital. Level 2, you have s and or shell 2. You have s and p orbital. For level 3, you have sp and d orbital. For level 4, you have sp, d, and f orbital. And you also need to know from general chemistry how many electrons, maximum number of electrons that goes to s orbital. We talked about already. 2 electrons is the maximum number of electrons that goes into s orbital. 6 is maximum number of electrons that goes to p orbital, and 10 is maximum number of electrons that is going to d orbital. 14 is the number of electrons that goes to f orbital. Number of atomic orbital, each of these, the s and p, they are also known as subshells. So we have 1 orbital in s subshell, we have 3 orbital in p subshell, and 5 orbital in d subshell. So each orbital takes maximum of 2 electrons. So if you have 5 d orbitals, each one is going to be 2 electrons. It adds up to 10 maximum. You need that in order to write electron configuration, like how many electrons would go to each subshell. How do you write electron configuration? We want to write electron configuration for carbon atom. A carbon atom is, I'm going to see if I can share with you something else at this point. Carbon atom has 6 electrons, right? With the 6 electrons, to write the electron configuration for carbon atom, we write in level 1, 2 electrons, so it's going to be 1s2. In level 2, you have 2 electrons in 2s2, and then level 2 has the other subshell, 2p2. So with the 6 electron is going to be 1s2, 2s2, and 2p2. There are principles that we have to follow, and that's another quiz question. Principles that is going to be followed in order to write the electron configuration properly. One is Aufbau principle. What does Aufbau principle states? Orbitals with lower energy is going to be filled up, first. So if you have the 6 electrons, the first electron is going to go to 1s. Why 1s? Because when you have your nucleus of the atom, then you have your first shell, second shell, and the third shell. The general idea is that the shells that are closer to the nucleus, they have lower energy. So you have N1, N2, N3. Levels that are closer to the nucleus with the lowest energy, they are going to fill up first. What do we have in level 1? Only one orbital, and that is the s orbital. Maximum number of electrons is going to be 2. So when we write 1s2, that's we are done with the level 1. There is only one orbital. This 1 as a prefix, it shows the level. S is the orbital that you have in the, or the subshell that you have in the level 1, and the subscripts of the 2 is number of electron that goes to the to that orbital. For level 2, we have 2 subshells, S and P. Maximum number of electrons that goes to s orbital is 2. Maximum number of electrons that goes to p orbital is 6. But since carbon has only 6 electrons, when we write 2p, we are going to count how many electrons is left that should go to p orbital is going to be 2, and that's why it ends up with 2p2. That is like electron configuration, like one rule to be applied to right electron configuration is the Aufbau principle. First, orbitals or the energy level with the orbital with the lower energy level must be filled up first before we can move to the higher energy orbitals. Your second orbital, second rule is the Pauli exclusion principle. Pauli exclusion principle from general chemistry. If you have two orbital, if you have one orbital, let's say you have a 1s orbital. For a 1s orbital, the 2 electron that is going to go to 1s orbital, if one is rotating clockwise, the other one must rotate counterclockwise. So no 2 electron can be placed in orbital with the same quantum numbers. So the quantum numbers are going to be different, or saying no 2 electrons are going to be the same. For the number of electrons that you have in the same orbital, they are going to spin with the opposite direction. That's the second rule. And the last one, if you have degenerated orbital, like what is degenerate orbital? Orbital with the same energy. When you have 2p, you have 3 2p, so we have to designate them as a 2px, 2py, and 2pz. When you are putting electrons in degenerated orbitals with the same energy, you have to make sure that electron 1 goes to the orbital 1, the first orbital first, then 1 electron in the second orbital, 1 electron in the third orbital, and then it goes back and pairs up if you have more electrons. So for carbon, because you have 2 electrons with in the p orbital, is going to be 2p, 1 in 2px, and 1 in 2py. Your 2pz actually is empty for carbon 12, or carbon with the 6 electrons. We have definition for core electrons and valence electrons. What's definition for valence electrons? Those are electrons in the outermost shell. And definition for core electrons, those are electrons in the inside shell. This demonstration or diagram, it shows the Aufbau principle. What does it show? Level 1 has 1 orbital only and is called 1s. Level 2 two subshell, S and P. Level 3, S, P, and D. As I said, the prefix shows the level and the symbol shows the subshell. Level 4 has 1, 2, 3, and 4. Level 5 is going to be 5. So it would be 5S, 5P, 5D, 5F, and 5G. So level 6 is going to be 6S, 6P, 6D, 6F, and 6G, and then 6H. So we have, based on the alpha principle, if you look at this line that is going diagonally, that determines which orbital is going to have less energy compared to the, and which one is going to be filled up first. So let's say I'm going to take an example of bromine with 35 electrons. I think I'm right with that. So 35 electrons. If I'm wrong, let me know. I don't have the periodic table open. So 35 electrons for bromine. The first level that is going to be filled up based on this diagram is going to be 1s orbital. How many electrons does it go to 1s? Thank you so much for your participation. What comes next? Based on this diagram, based on the diagram with the alpha principle, what comes next? 2s. How many electrons? 2 electrons in 2s. Very good. Which orbital comes next? So I complete this diagonal, that is the 1s. Then I went to 2s. Now I have to start with the 2p and then go to 3s. So this is going to be 3p. How many electrons? 6. Very good. And then comes to, after 3p, it goes to 3d or 4s. Which one should come next? 3d or 4s? 3. No. After 3p, you would say that 3d is in the same row or the same period of the periodic table because it's level 3, but based on the alpha principle that we have here, the 3d has higher energy than 4s. You follow this diagonal line. The 3p then goes to 4s, and then it goes back to 3d and then 4p. What comes after 4p? Would you have a 4d, 4f, or does it go to 5s? So if you can follow these lines, you are going to have proper electron configuration. So after 3p6, it comes 4s2, and I hope you all agree with that, 4s2, because only 2 electron goes to 4s. After the 4s, then it goes to 3d. And how many electrons does it go to 3d? We talked about it. We have 5 orbitals of d type in each level. Thank you so much for your answers. So we have 5 orbitals, and each orbital takes only 2 electrons. So maximum of 10 electrons is going to be to d orbitals in level 3. What comes after 3d is going to be 4p orbital. And how many electrons does it go to 4p orbital? 4p is going to take 6 electrons. Very good. Why did we go from 2s2 to? Oh, because it's too early in the morning. Did I skip? Thank you so much. Thank you so much. Thank you so much. I am really, really, really sorry. I'm going to start from writing again. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, because I concentrated so much on these exceptions that I forgot the 2p6 and the 3s2. They are going to be very upset with me. After the 4s2, it goes to 3d10, and after the 3d10 is going to be 4p6. 6. How many electrons we have so far? 4, that's 10, 12, 18, 20, 30. Okay, is 4p6 correct? Yes or no? Can I have 6 electrons in 4p? That's 10. 10. No, maybe not, right? How many electrons do we have totally for bromine? 35. And if we add up this, is a 2 plus 2, that's 4, plus 6 is 10, plus 2 is 12, plus 6 is 18, that's 20, that's 30. So our last orbital is going to be, our last orbital or subshell of p has to end up with 5 electrons only. So there is a stop point. We have to stop when we run out of electrons. We cannot just continue because we have all these orbitals for the Aufbau principle or the chart that we have. We have to stop when we run out of electrons. Very good. So I think with this like practice, we did practice the energy levels and how to use the Aufbau chart. We go with the 1s. The best thing is to be able to write this on a piece of paper, practice. Level 1 has one subshell, 1s. Level 2 has 2 subshell. So it would be 2p and, I'm sorry, 2s and 2p. Level 3 has 3s, 3p, 3d. Level 4 has 4s, 4p, 4d, 4f. Level 5 has 5s, 5p, 5d, 5f, and 5g. And then when you draw this, you just draw your lines diagonally, starting from 1s, go down. And then it's going to be 2s. After the 2s, go back up, and then it would be 3p, 2p, and then 3s. After the 3s, it goes to 3p, because this is the diagonal. After the 3p would be 4s. After the 4s is going to be 3d. The reason I draw this next to the Aufbau chart here, just to show you how easy and remind you how easy it is to draw the Aufbau chart. If you know that level 1 has 1 subshell, 2 has 2 subshell, 3 has 3 subshell, and you start with S, P, D, F, G, and then everything else is going to be alphabetic order, because at the beginning they were not thinking of 100 electrons. They were just thinking of the elements with the atoms with the low number of electrons. So then they had to go systematic and go to alphabetic order. So it jumps from F to G, and then it just goes to alphabetic order. Those orbitals exist, but they are going to be empty. Like carbon is in level 2, has only 1s, 2s, and 2p orbital. So if you have elements in level 3, only electrons is going to be in only limited number of subshells, level of 1, 2, and 3, because your element is in level 3. And you ran out of electrons, so you have to stop there. Okay, some electron configurations or examples of electron configuration. Hydrogen, you have 1s. Helium, we have 1s2. Lithium, just by addition of 1 electrons. For carbon, we have 1s2, 2s2, 2px1, and 2py1. This is another rule. If you have degenerated orbitals, the first orbital is going to take 1 electron. The second degenerate orbital has second electron. So I have more space here. I can draw the energy diagram for these electrons. So if the energy diagram, it goes up like this. I'm going to insert like one slide between the PowerPoint slides for starting tomorrow, so I have room to write. I didn't want to stop the class to do that right now. So we have level 1, you have 1s, then you have your level 2, is 2s, and then you have your 2p, 2px, 2py, and 2pz. This energy level, so if you look at this line as the amount of energy that you could have for each orbital corresponding, so if you continue this to cut this line, it represents the amount of the energy. 1s has less energy than 2s, 2p has less energy than 2s. Why 2p has less energy than 2s, even though they are in the same energy level? That goes to shape of the orbital. The shape of the orbital for s is spherical. Electron can reside in there much easier because there is no restriction, but p orbital is a dumbbell shape. So electron really cannot stay here, cannot stay here. These are the two loops that electron can stay in there or can reside. So it makes it a little bit harder for electron to be in specifically in these regions of the loops up and down, but for s is easier. So for each energy level, s is going to have less energy than p. So 3s is going to be less energy than 3p, and 4s is going to be less energy than 4p. When it comes to d orbital, they are even more complicated. So this is like a S shape for S, this is shape for P, but for d orbital, let's say for a, this is just one d orbital. So for electron, cannot be here, cannot be here, cannot be here, cannot be here, but it could be in one of these loops. So because it's more complex shape, this is the easiest way to explain. For the, is going to be, it has more restrictions, and because of the high restriction for d orbital, the electron being in d orbital must have more energy. So for electron to be in s orbital, 1s orbital, is going to have the lowest amount of energy required. For the 2s is going to be a little bit higher, and you go further away from the nucleus, the energy of the level, the shell, subshell is going to increase. So for electron to be in level 4 must have a lot more energy than the electron in level 2 and electron in level 1. So going back to the carbon, again, energy diagram for carbon with the 6 electron, the first electron is going to go to 1s. And this arrow is showing just the spinning clockwise or counterclockwise. Second electron would go to 1s. Electron number 3 is going to go to, where would it go? To 1s or 2s? 2s. Why not 1s? Because 1s is already occupied, it's sold out. And if it's sold out, it's full, we cannot put the third electron in there. So electron 3 must go to 2s orbital. Electron number 4, where should it go? Electron number 4 has a choice of 2s or 2p. Okay, I had two responses, 2p and 2s. Why not 2p? Which one has lower energy? 2s has less energy than 2p, and because it has less energy than 2p, 2s needs to be full first. That is based on the Aufbau principle. So we go to 2s. Now, electron number 5 would go to 2px because 2s is already full. Very good. Thank you for your response. Electron number 6, where would it go? 2py. This is the second rule that we have to apply. These are degenerated orbital, and the reason I draw this energy diagram for you is to show that 2px, 2py, and 2pz, for the best estimate, they are in the same energy line. So the energy corresponds to this point of the graph. So they have same energy. So for electron to have a choice to go to 2px or 2py, is going to go to 2py because of that Hans rule, or the second rule, is going to go to the 2py. You can memorize that, or you can justify it. What is preventing electron 2py to go to 2p, this electron number 6 to go to 2px? Anyone can explain that? Why is easier for electron number 6 to go to 2py and not 2px? I give you a hint. What's the charge of electron number 5? The charge for electron number 5? -1. What is the charge for electron number 6? Also negative, right? One negative electron charge for electron 5 and electron 6. So how same charges, they repel each other. Opposite charges, they attract, right? So for electron number 6 to go to, if this is my electron number 6, to go to 2px, must tolerate the negative charge from the electron that is already there. But if it goes to 2py, there is no repulsion. So it's going to be more free. It's like when you step into a bus and you see like the seats are like double seats next to each other, and then you have different rows. And if the first row has only 2 seats, that's like a 1s occupying 2 electrons, two people is going to sit there. But in level 2, let's say you have 2 sets of 2, and then the first set is occupied by 1, the second set is not occupied. You probably would like to go to seat where is not occupied, the pair of the seats that is not occupied, because you don't want to be hindered, bothered, or you don't want to bother the other person. There is an exception unless the person who's sitting there, you know them, you have some sort of attraction toward that person. But believe me, electrons both carry negative charge, and since they carry negative charge, they have no attraction toward each other. So it's going to take the one that has no person in there, is empty completely before forcing to go to one that already has one person. Now, to continue with that, I'm going to continue with fluorine. Fluorine has 9 electrons. Okay, 9 electrons for fluorine. So if we just keep this as the electron configuration based on the energy orbital of carbon, I'm going to use the same diagram. You can draw a new diagram. For fluorine, we have 9 electrons. So electron number 7 is going to go to 2pz. Electron number 8, where would it go? 2px. Very good. 2px. Why not 3s? Because electron to go to 3s must have more energy than, no, yeah, sp is not full, but to justify that, electron number 7 has 2 choices, either to go to 2px and pair up with the other one to be the second one, pair up, must tolerate the other electron, or to go to 3s. 3s has higher energy than 2px. So it's going to go to 2px, but you know what's going to happen? It's going to turn around, say, okay, you're sitting here, even though I don't like you, but I'm lazy enough, I don't have the energy to go to 3s, so I'm going to just sit next to you, and because of your negative energy, I'm just going to turn around. That turning around is not nice, but at least it can justify why they have opposite spin. So it's going to occupy the 3px, but with opposite spin. That is the other rule, the Pauli exclusion principle, that it says no 2 electrons in the same orbital can have same quantum numbers. So if all 3 of them are the same, if they are in the same energy level, they are in the same orbital, they must have different spin number. So electron number 8 would go to 2py. And that is the energy diagram for fluorine with 9 electrons. Do you have any questions about electron configuration? configuration. The good thing about organic chemistry is that you're limited to level 2, elements in level 2. So if you know electron configuration after fluorine, then you're fine. Do you have any questions? No questions? Okay. Now, we talked about the atom, subatomic particles. We talked about electron configuration, writing or drawing electron configuration based on the Aufbau principle, Pauli exclusion principle, and Hund's rule. Orbitals with lower energy is going to be occupied first in full. Orbitals that they have same energy would be occupied singly first and then starts pairing up. If you have 2 electrons in the same orbital, they must have opposite spin. Why do we need the electron configuration? Because when we talk about sp and sp2, sp3 hybridization, we need that electron configuration. We will get to that. You learn that in general chemistry, but we apply it in organic chemistry. Now, we are moving to next slide, which is bonding. How many different type of bondings you have between 2 atoms? Or the 2 atoms, how they can form bond with each other? Any answers, or should I say it? You have 2 types of bonding. One is ionic bonding and the other one is covalent bonding. What is ionic bonding? Ionic bonding, for ionic bonding, ions form first and then there's electrostatic attraction between the ions. So if sodium loses 1 electron, it's going to change to sodium ion plus 1 electron. Why sodium is losing an electron? Because sodium is in group 1A, has 1 valence electron, and in order to be stable, like neon with 10 electron, it must lose 1 electron. So it's easy for sodium to lose electron. Chlorine has 17 electrons. With 17 electron, if it wants to be like neon, it must lose 7 electron. But it wants to be like argon. Argon has 18 electrons. So for chlorine, it's much easier to gain 1 electron and to be negatively charged, Cl minus. What happens if you have opposite charges? When you have opposite charges, it's going to be very strong attraction between them. And this is attraction between the why is not showing the okay, a strong attraction between the opposite charges. So ions for first, and then there's electrostatic attraction between the opposite charges. That's why it's called ionic bonding. That means the bond between ions with opposite charges. So Cl with sodium or potassium with chlorine or any metal with non-metal is going to form ionic bonding. Hydrogen bonding. Good question, Ariana. Hydrogen bonding is not a intramolecular force. With the intramolecular force, that's the bond between the 2 atoms in the same molecule, we have ionic bonding and covalent bonding. The other type of bonding that we have, or we can classify, which I'm going to go over when we talk about covalent bonding, is that you could have polar covalent or non-polar covalent. So if we have ionic, if we have polar covalent, or non-polar covalent, ionic is between metal and non-metal. So polar covalent is between 2 non-metals that they are different from each other, just like hydrogen with chlorine. Which one has higher electronegativity? Based on position of chlorine in the periodic table, chlorine has more electronegativity, so it's going to pull the electrons toward chlorine. Electron is going to spend more time around chlorine than the hydrogen. So hydrogen is going to be a slightly positive, chlorine is going to be a slightly negative. This is covalent, but is polar covalent. Non-polar covalent, it happens between the two of the same atom. So chlorine with another chlorine, they both like electrons. When they share electron, they are going to share electron equally or evenly, and that's what makes it non-polar. These three types, 1, 2, and 3 type of forces is called intramolecular. That happens between the two atoms of the same molecule. To answer your question about hydrogen bonding is between hydrogen of one molecule and oxygen of another molecule. That is known as intermolecular forces. So when we talk about intermolecular forces, you could have hydrogen bonding, dipole-dipole, and you have van der Waals forces, and I'm sure we are going to talk about those. But just the sharing of electrons between the two nonmetals. When you have hydrogen and oxygen forming bond, they are going to share electron. Why? Because they both like their electrons. They are both nonmetals. They don't want to lose electron, but in order to satisfy Octet's rule, they are going to share electrons. So oxygen, look at these patterns because you are going to need this. We are not talking about general chemistry. We are not learning about only the covalent bonding and the Lewis structure. We are looking at the application at this point. You see, carbon, when it forms bond with 4 hydrogen, is going to have CH, H, and H. How many bonds do we have around carbon in CH4? 4 bonds. And these are called sharing electrons, right? These are shared electrons. Shared electrons are not very reactive because they are engaged already between the two nucleuses. They are very stable. For this bond between the carbon and hydrogen here, this pair of electron is shared between hydrogen and carbon. They are loved by nucleus or attracted by the nucleus of hydrogen, and they are attracted by the nucleus of carbon, so they are stable. When you write oxygen or compound containing oxygen, you see there are 2 pairs of electrons that they are not shared. So these are unshared pair of electrons, and that makes the molecule more attractive for organic chemistry. So for example, when you have alkyl halide, so oops, that's okay. So when you have alkyl halide, you change that with chlorine with 3 pairs of electrons, and you have the hydrogens, carbon with no pair of unshared electrons. You have 3 pairs of unshared electron here. That makes chlorine very different from carbon because it has 3 pairs of unshared electron, and that makes the molecule unique because with element with 3 pairs of unshared electron now can act as a nucleophile. It can attack something else. And when you have oxygen, you have 2 pairs of unshared electron. So where do you find oxygen? If you know from 1046 or you know in your other information, you could find them in like alcohols, right? And alcohols, CH3, OH. This one has 2 pairs of electron. Comparing CH4 with no oxygens, this one is CH3OH, oxygen with 2 pairs of unshared electron, chlorine with 3 pairs of unshared electron. Alkyl halide is more reactive than alcohol. Alcohol is more reactive than methane or CH4. So these pairs of unshared electrons, it makes the molecule unique. And it makes it unique because they can now act as nucleophiles. A positive charge, partially negative charge. Anything that you see in the molecule is going to give this carbon partially positive charge because it's pulling electron also. So it makes this molecule to be more reactive compared to the CH4. Okay, nitrogen. You get one pair of unshared electron on nitrogen. This is the Lewis structure for methane, and then we have the Lewis structure for NH3 or ammonia. I am going to practice one Lewis structure. Looking at the time, I'm going to, I think our class ends at 9:45, so I'm going to leave the 5 minutes, last 5 minutes for the questions. So in the 2 minutes that we have, I'm going to draw the Lewis structure for one molecule just to practice and review from the general chemistry. So let's say I'm trying to write the electron configuration. I'm sorry, trying to draw the Lewis structure to start from scratch. What should I start with? I'm going to start with SO2. First, you draw the backbone of the molecule, sulfur, and then oxygen and oxygen. Why did I put the sulfur in the center? Because central atom is unique. Central atom must have lower electronegativity compared to the side atoms. Central atom cannot be hydrogen. Central atom cannot be chlorine or halogens. Central atom has lower electronegativity compared to the side atoms. So that's how you choose your central atom. And then you put your other elements around it. Count the valence electron, because for Lewis structure, you only use the valence electron. How many valence electron we have for sulfur? 6 valence electron for sulfur. Oxygen, we have 6 valence electron for each oxygen, so it's going to be 6 times 2. In total, I have 18 electrons. So I start with the 18 electrons. First, I have to connect these. These are the steps for drawing Lewis structure. First, connect them. How many electrons did I use to connect? 4 electrons. Each dashed line represents 2 electrons. Thank you so much, Jordan, for your response. So two electrons for each dashed line. So it adds up to 4 electrons. So I'm going to use electron and subtract. I have now left with 14 electrons. With the 14 electrons, who is going to get electrons first, the central atom or the side elements? The side elements, they have higher electronegativity. Because electrons in the side, they have higher electronegativity, we have to satisfy the side electrons first. How many electron oxygen? I'm going to call this oxygen 1 and this one oxygen 2. How many more electron oxygen 1 needs to satisfy the octet? Already has 2. Very good, very good, very good, Melanie and Jordan. 6 more electrons. So 6 more electrons we need for the oxygen 1 to satisfy. How many electrons do we need for oxygen 2 to satisfy? Because we already have 2 electrons, thank you, we put 6 more electrons. How many electrons did I use in total to satisfy the oxygen? Is 12 electrons. So I use electrons, I'm going to subtract. How many electrons is left? Is 2 electrons left only. So my side elements are satisfied. The 2 electrons that are remaining, I'm going to give it to central atom. How many electrons is left? 0. 0 electron is left. Am I done with this structure? No, thank you. No. I have to go back and make sure that every element is satisfied with 8 electrons. If there is element that is not satisfied with electron or 8 electron, we have to use multiple bonding because they have to deal with it. When you have covalent bonded compound, it's like a family. They all put their money together. Let's say you have like $18 here, and then I usually use the mom and 2 kids example here. Sulfur as a mom and the 2 kids, the 2 oxygens, they walk to McDonald's. They have to first hold hands. So we have to put these two bonds, that takes energy. It takes, I call it like it takes energy they have to watch for each other to make sure they're connected. 4 electron or $4 consumed there. Children is going to order their Happy Meal first. And if they order their Happy Meal $6 each, $12 is gone, only $2 is left. With the $2 that is left, mom can only order maybe a side, or mom can order just a drink. And no money is left. What's gonna happen? Kids, they have their Happy Meal, mom stays hungry. What would be fair? Because they are family, they are going to take care of each other. And mom only needs 2 more electrons, right? Or just sharing like with one of the children. If they are going to share, they are going to take the 2 electrons. We are going to take 2 electrons from side and bring it to the center. So now the central atom, or the mom, has enough electrons. So before we had only 6 electrons for sulfur, now we have 8 electrons for sulfur. If the same thing happens another day, most likely the other child is going to share, because that's how families work. Everybody is going to share. So with this, 2 with respect to each other, each one of them is a complete loose structure. Why do we say complete loose structure? We have used all electrons, and each element is happy with 8 electrons. Oxygen 2 has 2 pairs of shared electron, 2 pairs of unshared electron. Oxygen 1 has 3 pairs of unshared electron and one pair of shared electron. And sulfur has 1 pair of unshared, 3 pairs of shared electron. Each one is satisfied with 8 electron. When we come to the second resonance here, these 2 structures with respect to each other, they are known as resonances. Now oxygen 2 has 6 electrons that is not shared, 2 electrons shared. Oxygen 4 has 4 electrons that is unshared, and 4 electrons that is shared. We will continue with the resonance structure, and when we are using it, I'm sorry, I promised I'd give you time for questions, but it's 9:45. I don't know how many of you have labs today, but I am here to answer your questions. We will continue from here. I know that I didn't have enough room on each slide to make sure that my writing is going to be more clear, because this is going to on recording, but you are expected to have your own notes anyway. Make sure to print those if you have access to printer or Notability, or even if you don't, just make sure to take paper and pencil and write down your notes. Please do not depend on the recording. Do not depend on the recording of each lecture. Because I recorded the lecture, it should be available after the lecture is over. So we should be able to find the recording. It's going to be archived in D2L. So you should be able to locate it when you go to the Blackboard Collaborate. Other questions? Multiple choice. Your exams, good question. Your exams is going to be multiple choice and short answers, and free response questions. Your quizzes, most of them is going to be multiple choice, but you do practice your free response questions using the OR app, the assignments, and the co-ops to prepare for the exam. Most of the question is going to be multiple choice, unless there is a need to show that you have to know, like one of these questions as a written question. So the exams will be recorded. Yes, exams is going to be. Let me see what. I missed the last question. What was the last question? So Exams will be recorded. What do you mean by exams will be recorded? If you mean that it's going to be proctored, yes. We have the honor lock, which is the highest so far security that they have came up with, that monitors the room, monitors your devices that you have in the room and all that. And then we have Respondus. Respondus is cheaper than the honor lock, but still it's going to check your ID to make sure that you are the one taking the test, and also take your picture and all that. And it will lock other screens. So you would only be working with the exam. Do we take the quiz during the class time, or are they due at the end of the day? I was thinking about this morning. I didn't come up with a solid answer, but I'm going to ask the class, what do you think? Should we have the quiz the first 15 minutes or the last 15 minutes? Or I think the last 15 minutes of at the end of the day. Perfect. At the end of the day. Very good. End of the day. So now it doesn't have to be the Broward ID, as long as it's a government approved ID, driver's license, it should be fine, or any school ID is fine. For your lab today, are we having live sessions? Yes, live sessions, because we don't have a approved online course for the organic lab. So it's going to be based on the syllabus. It's not going to be long. The lab is going to be most likely like 45 minutes, most likely. And let me do this. Let me